Light in its natural state is scattered and chaotic, but when forced through specific boundaries, those beams reorganize into a rigid geometric grid. This symmetry is a direct result of three basic materials aligned according to the laws of physical optics. The required inventory is minimal: an outer tube, a rotating object chamber, a translucent diffuser, and a prism made of three plane mirrors. The difference between a blurry reflection and an endlessly repeating fractal comes down to the precise physical tolerances of these specific raw materials. Standard household mirrors are second surface mirrors. Light passes through a layer of glass before striking the reflective backing. That journey through the glass absorbs energy, meaning only 80 to 85% of the light is actually reflected, creating a faint secondary image known as ghosting. A precision optical instrument requires a first surface mirror. Here, the reflective coating is applied to the top layer. Light bounces directly off the surface, returning 94 to 99% of the incoming energy. That 10% difference dictates the viability of the entire system. When light bounces back and forth dozens of times inside a closed tube, even a small drop in efficiency compounds, causing the image to fade. To construct a prism capable of producing sharp, recursive patterns through multiple levels of reflection, the internal surfaces must bounce light with near total efficiency. We begin by binding three first surface mirrors together, reflective sides facing inward, to form a hollow, triangular prism. The precise geometry of this prism defines the final image. For this build, each of the three mirrors is set at exactly 60 degrees, creating an equilateral triangle. We enclose this prism inside an outer housing and attach a rotating chamber at the end, filled with translucent pieces of colored glass, which act as the visual raw material. To illuminate those objects, we cap the end of the chamber with a frosted diffuser. This layer softens harsh ambient light, ensuring the objects are lit evenly. The tube and the colored glass are merely support structures. The true mechanism is the geometric light trap formed by those three angled mirrors. This diagram illustrates the fundamental law of reflection. As light enters the prism, the angle of incidence exactly equals the angle of reflection, and every ray rebounds along a predictable mathematical vector. This grid charts the optical system's golden rule. The angle between intersecting mirrors must divide evenly into 360 degrees. At 90 degrees, it divides 4 times, yielding a 4-point symmetrical pattern. Our 60-degree build divides 6 times, tiling a continuous hexagonal pattern. Tightening the angle to 30 degrees produces a more complex 12-point mandala. Mathematical precision dictates the visual result. Any angle that fails to divide evenly into 360 will cause the patterns to overlap, fracturing the illusion of continuous symmetry. When looking down the assembled 60-degree prism, the loose fragments of colored glass resolve into this: a flawless, repeating star radiating outward with mathematical precision. The physicist David Brewster codified these principles in 1816. Decades later, designers evolved his concept into a device called the telescope. A telescope removes the enclosed chamber of colored glass entirely. Instead, the end of the mirrored tube is left open and capped with a clear fisheye lens. This convex lens captures a wide field of view and compresses the external world into a dense focal point, feeding the ambient light directly into the same 60-degree mirror trap. The laws of reflection aren't limited to internal objects. They can capture any external environment and mathematically organize that reality into structured art. The radial patterns generated by this instrument mirror the macroscopic structures found in the natural world, from the geometry of a snowflake to the arrangement of a flower. We see these identical proportions replicated in human engineering, from Islamic geometric tiling to Gothic stained glass windows. Whether observing the lattice of a mineral or a vaulted cathedral dome, the resulting symmetry is governed by the same geometric constraints we built into our tube. The kaleidoscope functions as a mechanical translator, taking chaotic light and reordering it into a structure defined by predictable geometric constraints.